Right. So the first of our Extension 1 actual topics, we've looked at a couple of bits and pieces of Extension 1 work, but this topic as a standalone topic is purely extension work, and it's the idea of permutations and combinations. And what we start off with is looking at, as the name suggests, a very basic idea, a basic counting principle. You may remember when you're doing probability and you end up drawing tree diagrams or sample spaces and things like that. And that really does limit you as to the sort of problems you can solve. And in reality, we don't really need the tree diagram. All we're really interested in is how many outcomes there are, because that would be on the bottom of the probability, and then how many possibilities for what I want to happen, which would be the top of the fraction. So if we can work out how to count that, rather than having to draw it up, we can save ourselves a lot of time. And that's what the basic counting principle basically says. If an event happens in m different ways, and then after this another event happens in n different ways, then all up we have m times n. Because if you think of your tree diagram, if you were to draw m branches, and then off each of those you had n branches, you would end up with m times n. There's no need to draw them all. All we're really interested in is how many there are. And that's the basic idea. So, okay, 3 dice. See, 2 dice, yeah, it's easy enough to draw up the sample space. You just draw them all out. There's only 36 outcomes, doesn't take too long. 3 dice is now a lot more to draw up. It would take a long time. So 3 dice are rolled. How many ways can the 3 dice fall? In other words, how many different outcomes if we were to write them all out? Well, using the basic counting idea, well, the first dice, there would be 6 ways. And then we'd branch off for the second dice, there'd be 6 ways. And then the third dice, 6 ways, so 6 cubes. We'd end up having 216 branches, or 216 possibilities, if we were to draw up the sample space. Obviously not something we want to do. But if we were interested in saying, oh, well, okay, but what about if all 3 dice show the same number? So using the basic counting idea, I can say, well, hang on, if I roll the first dice, it could be any number. So there's 6 different things, the first dice. But once I've got the number, I want all 3 to say the same thing. So now there's only 1 possible outcome for the second dice. And the third die also only has 1. So all up, 6 possibilities. So if I now was to ask, well, okay, what's the probability that all 3 dice show the same number? Well, then it's simply 6 number of possibilities over total number of outcomes. We worked out 216, and we have our probability without having to draw up the whole sample space, and that simplifies down, of course, to a 1 in 36 probability. Here's an HSC question from a while ago now. So mice are placed in a maze. The maze has 5 exits. Each mouse is equally likely to leave through any of those 5 exits. Thus, the probability of a mouse going out a given exit is 1/5. 4 mice, conveniently named A, B, C, and D, are put in the maze and behave independently. What's the probability that A, B, C, and D all come out the same exit? Now, I can do it via probabilities rather than just individual counting, because I'm just doing the possibilities and the number of outcomes all in one hit by doing probability. So the way I do this, probability they all use the same exit. Well, the first mouse could go through any door. So there's a probability of 1 that it could leave through any exit. But then once we've done that, we've said B, C, and D all go out the same. So there's a 1 in 5 chance that B goes through that same door, a 1 in 5 chance that C goes through the same door, a 1 in 5 chance that D goes through the same door. And so that equals 1 in 125. That's equivalent to using the basic counting idea, because had I used the basic counting idea, I would have said, how many total possibilities are there? Well, the first mouse could go through 5 doors, second one 5, third one 5, the fourth one 5, so it'd be 5 to the power of 4, total number of possibilities. How many where they go through the same door? Well, there's 5 doors for the first mouse, but then 1 for the second, 1 for the third, 1 for the fourth. So it'd be 5 over 5 to the power of 4, which is, of course, the same as 1 over 125. What's the probability that A, B, and C come out the same exit and D goes out a different one? Okay. So A, B, and C are now going through the same one. Whenever I'm doing these, I look after the conditions first. So A, B, and C are going through the same door. So D, if you like, it's the one that's going out through the different exit. So I'll let it go first. There's a 1 chance, probability of 1 that it leaves. So now A, B and C, they're all going to go out through the same door. So A comes along. Well, it's got 4 doors to choose from. It can't go out the same door as D just left. So there's a 4 in 5 chance of it leaving. But then the next mouse comes along, or the next 2 mice come along, and they both now have a 1 in 5 chance because they've got to go through the same door as A went through. And so we have 1 times 4/5 times 1/5 times 1/5, 4 in 125. It then said, well, okay, but what's the probability that any 3 of the 4 mice go out the same exit and the others go through a different exit? We just worked out the probability that D uses a different exit is 4 in 125. Well, A, B, C and D were just letters. I could have picked any letter. So logically then, the probability that A uses a different exit would also be 4 in 125. B uses a different exit would also be 4 in 125. C uses the same different exit, 4 in 125. So therefore, the probability that any mouse uses a different exit to the other 3 must be 4 lots of 4 in 125. So 16 lots of. What's the probability that no more than 2 mice come out the same exit? So no more than 2. Well, probability of no more than 2. I'm going to use the complementary idea. You remember in probability, sometimes it's easier to work out what you don't want and then subtract it from 1. And that's what I'm going to do here. Because no more than 2, well, the opposite to that would be all of them going through the same exit or 3 of them going through the same exit. We've already worked out both of those probabilities. Okay? Remember, the first question was they all go through the same door. That was 1 in 125. The one we just did was any 3 go through one door and the 4th goes through another one. So I already have those answers. It can save me time in this case by using our complementary events idea. So we get 108 over 125. All right, so that's the basic counting idea. But we're really interested in this topic in specific types of situations, permutations and combinations. So first of all, we're going to look at permutation. And what is a permutation? It's simply an ordered set of objects where the order of things happening is important. So me picking up this black texture than this blue texture would be different to me picking up the blue texture than the black texture. Okay? The order is important. So our first case, we've got n. So we're going to generalize. We've got n different objects. So imagine over there in the corner there's n objects. And they're all different. Right? So n different objects from a set of n different objects. We're going to use all of them. This is what that's saying. I'm going to select a set of n objects from a set of n objects. Well, how many ways can I do it? So I'm going to get these n objects, arrange them in a line. So I'm going to go over here to my n objects and say, oh, look, one of you, I want you to go over there and just stand. How many ways could I pick an object? N. There's n objects. Okay, so the first one, bang, got them. They're now standing there. I now go over to the pile and go, look, yep, I need another person. How many have I got to choose from? N minus 1. And then I could keep going. N minus 2. But I'm going to use all of the objects. So eventually I'm going to get to a point where I'm going to go over to this pile and there's only going to be one left. I say, look, okay, you just go join the line. And there'll be just one way I could do that, that very last person. So n times n minus 1 times n minus 2 all the way down to 1. Now you may remember in mathematics we have a notation for that to save us writing n times n minus 1, and that is our factorial notation. And so there's n factorial ways of arranging n different objects. In how many ways can 5 boys and 4 girls be arranged in a line if there's no restrictions? Well, if there's no restrictions, boys, girls, doesn't matter. I'm just arranging 9 objects, so 9 factorial, which is a lot, by the way. But much more fun if we put restrictions in it. The boys and the girls alternate. All right. If the boys and the girls alternate, how many ways of doing it? Always look after your restrictions first, the things that are causing you problems in working out the number of arrangements. I've got to work out whether I'm going to select a boy or a girl to start off with. Now, I must start off with a boy. Because if they're going to alternate, I'll run out of girls if I start with a girl. So there's only one way I could start this line. I haven't actually arranged anything yet. All I've done is I've decided whether I'm going to choose a boy or a girl. Okay, so I'm going to look after the boys first. There are 5 boys. Okay, fellas, go and arrange yourself. Will you do that for me? Thanks. 5 factorial ways of it happening. I now go back, I've got to arrange the girls. I said, girls, sort yourself in order, but when you go and stand in that line, just slot in between the guys. So 4 factorial ways of arranging them. So all up, 2,880. Arrange boys, then arrange the girls. Had there been the same number of boys and girls, then I would have said 2 times, because I would have had an extra choice then. Do I start with a boy or do I start with a girl? And so it would have been 2 times, let's say there was 4 of each. 2 times 4 factorial times 4 factorial. What then is the probability? So here comes the basic idea of this is to save time. I don't want to draw a tree diagram up with all those possibilities, those 300,000 or whatever it was. So the probability that they alternate then is simply, well, okay, 2,880 of them was the alternating ways over total number of possibilities. There's my probability. 1 in 126. Okay. But what happens if now, we'll put a different condition on it. 2 of the girls wish to be together. Okay? Now, these 2 over here have said, I want to be together. See? So they're over here. Look after the restriction first. Okay, girls, you want to be together. Sort yourself out. Which way round do you want to go? Well, there's only 2 of them. So there's 2 factorial, or 2 ways they could stand. They haven't been arranged yet. All we've done is we've sorted out how they're going to stand. But once we've worked out how they're going to stand, they now become a group. They're like they're one object. And so now I'm going to arrange that one object of 2 girls and the 7 other people. So there's 8 objects I'm now arranging instead of 9 objects. So 8 factorial. 2 factorial, 8 factorial, 80,640. Okay, so that's if we use all of them. But what happens if we don't? So k different objects from n objects. So k obviously is less than n. I'm not going to use all the objects. I'm only going to use some of the objects. How does this change the problem? Well, to start off with, it's not going to change the problem. I go and pick that first person, there's still n of them in my pile. Go get my second person, there's still n minus 1. Go get my third person, there's n minus 2. But I'm going to get to the last person I'm going to pick. Remember, I'm only choosing k of them. So I'm going to go choose my kth person. How many ways could I choose my kth person? Have a look at the pattern. First person, n ways. Second person, n minus 1. Third person, n minus 2. So logically, kth person would be n minus k plus 1. Okay? But again, that's a little bit confusing, so we can use factorials to simplify this. If I multiply top and bottom by the missing ones, in other words, the number of ways I could have arranged those people if I wanted to, then what I've ended up getting is n factorial over n minus k factorial. So what in reality has happened is said, well, if I had arranged them all in a group, there would be n factorial ways of doing it. But I'm going to divide it by the ways that I didn't use. Those n minus k factorial people over there, I didn't use those arrangements, so I'll divide by the n minus k. So that's a way of thinking of it. This has a notation, P for permutation. NPK, which on some calculators is on the multiplication or division button. Not sure. Some have it on one of those. Some have a different function for it. So it can save some time. We can plug straight into our calculator. But it is still important to know the actual definition Because sometimes if we're doing problems where it's not an actual number, it might be just n people and so on, we're going to need to know the definition. Let's try it. Here we go. Problems. Seeing we're looking at problems, let's look at problems. There's the word problems. How many 5-letter words are possible? And remember, this is not English, this is maths. So when we talk about 5-letter words, any arrangement of 5 letters is a word as far as a mathematician is concerned. So how many ways? Well, there are 8 letters. I'm only going to arrange 5 of them. So that's 8p5. 8p5. Or 6,720 different words. In factorial notation, that would have been 8 factorial. That's the number of ways I could arrange all the letters divided by 3 factorial. Yeah, 3 factorial. Number of ways I could have arranged the letters I'm not using. Let's put some conditions on it because that's much more fun. The words must begin with P because we like P and we're going to start the word with P. So we look after the condition first. How many ways can we start the letter P? Well, 1. I start with P. There's only one way I can do it. So now the question becomes, how many 4-letter words from problems? I've used the P, but I still need to get another 4 letters to go after it. So from the 7, I'm going to arrange 4 of them. So 7p4. 840. Okay, let's get even more fun. Here we go. P is included, but not at the beginning this time. And M, we don't like M. Excluded. Not using that letter today. Okay, look after the conditions. P, I'm going to place first, but there's only 4 spots I can put it. Can't put it in the first spot, but it could be the 2nd letter, the 3rd letter, 4th letter, or the 5th letter. So there's 4 ways I can place P. Okay, P is now put in. I'm going to put in the other letters, so I've got to arrange another 4 letters from, oh, hang on, not allowed to use M. So it becomes 6p4, because we're now saying, how many 4-letter words from Robbles? We got rid of M. Not there anymore. So 1,440. Okay, we're in a boat. 6 people, in fact, are in our boat. There are 8 seats in this boat. And like I said, this is maths, not English. 4 on each side. What's the probability that Bill and Ted are on the left side and Greg is on the right? Okay, if I want to work out a probability question, for the bottom of the fraction, I just need total number of ways with no restrictions. So how many ways can I place these 6 people in the 8 seats? 8p6, because the order is important. So that will end up being on the bottom of my fraction. Now, we need to work it out. Okay, Bill and Ted are being awkward. They want to be on the left. How many ways can we do that? There's 4 seats on the left. Going to use 2 of them. So 4p2. Now, Greg says, well, if they're on the left, I'm going to go on the right. So 4p1, which turns out to be 4 actually, can go on the right. Then the other 3 people just say, you guys are stupid. The seats are set. We'll go anywhere. So how many seats have we got left? We've used 3. There are 8 all up. I've got 5 seats left. I've got to seat 3 people. So times 5 is p3. So there are 2,880 ways of doing it. Well, the question is, what was the probability? So 2,880 over 20,160, a 1 in 7 chance of it happening. A 1 in 7 chance. Okay, here's another HSC question. Sophia has 5 blocks. A red one, a blue one, a green one, a yellow one, and a white one. She stacks towers. Now, you can't have a tower of 1 because 1 would just be a block. So towers can only be 2, 3, 4, or 5 blocks high. So the first question, how many different towers are there that are 3 blocks high? So from the 5 blocks, because they're different colours, the order that I pick them will make different towers. So 5p3. 60. Well, how many different towers all up? That was just 3 block towers. Well, 2 block towers would have been 5p2. 20. 3 block towers we just worked out, 60. 4 block towers would be 5p4. 120. 5 block towers, 5p5. Also 120. So all up, there's 320 different towers that could be made. All right. 10E. What's up?